All right, class, let's come to the third lecture for chapter one, which will have a discussion about energy method to formulate FEA equation. Okay, let's go to the next slide. Here it's a short summary what we have learned so far. Last lecture we learned stiffness method, which is a straightforward method, well, suitable for simple geometric scenario. But when system become complicated, and energy method, which we'll learn today, will become a much better method. So energy method is also sometimes called a variational method. Okay, and then let's have a review what we have learned in last lecture. In last lecture, we start from a problem that if we have a structured material and we apply force on its surrounding, as shown here. So if there's a circular hole in the middle, and theoretical solutions become very difficult. So then we need to turn to FEA method. For FEA method, finite element analysis, and the first step is to mesh it. So once we mesh it, we get a bunch of elements, and then next step, we look at one element. So in this case, this is a 2D, and you can imagine that there will be 4 nodes, and each node has 2 freedom. It can go X direction, go Y direction. And then in this step, we will establish a relation between the displacement as well as the force applied on the node. So if you uh, look at this, let me write it down. If you look at this F is a force applied on the node. So at each node there will be a force, and it can be has X component and Y component. And then we apply force to it, there will be displacement on the node. And based on the force relation, and we can generate a stiffness equation, and for this element, which is a K is the element stiffness matrix times U is the displacement vector, and for this 4 nodes, and F is the external force applied on the 4 nodes. Well, you can imagine there will be many local matrix equations for each element, and then we assemble it, and if we assemble the local or element equations, and it will become a global matrix equation. So it depends the number of elements, and it will generate a larger scale matrix equation. So K will be a global stiffness matrix, and U is global displacement vector. So, and depends how many nodes we have, and this there will be how many vectors, how many elements out times the freedom. Like X, Y direction, there will be 2 freedom, and then the node will have a size like the number of elements times 2. So you can imagine there will be a pretty large matrix equation, but computer is good at dealing with matrix equation, they can solve it. Well, that's a review of stiffness method. So, and this is a quiz problem we have worked on last lecture, and let's have a quick review that how to work on that. So in this problem, we have 3 springs. So we have a spring system, and the basic element is one spring. So last lecture, why stiffness method, we are able to establish the local or element equation for each element. So, and for each spring, in this K stiffness equation will be K1 minus K1 and minus K1 and K1, and then times displacement for element 1 or spring 1, and the node we have here is node 1 and node 3. So that means for the displacement vector we have U1, U3. And then for the force, so we have force acting on node 1 and force act on node 3. So the subscript represents the node, and we also put a upper subscript to denote that this is for the first element or spring 1. Similarly, we can set up the local equation, and for node 2, which is U2, U3, and then time equals second spring on node 2, second spring on node 3. And the last element, which is K3, and we have a similar equation, and we'll move a little bit top because not much space for it. K3 minus K3, and then we have U3, U4, that's a node for spring 3, and equals force, node force F3, F4, of course, this is for spring 3. Okay, and then we have this 3 local equation. And the last step is assemble the 3 equations together. We'll get a global equation. And for that global equation, we'll have global K and times U1, U2, global displacement. We have 1, 2, 3, 4 node, and this is a 1D problem. It's only have one direction, so we have 4 nodes, and we have 3 nodal forces: 1, 2, 3, and 4. That is the nodal forces acting on each node. And this K, well, when assembling, the K part is assembling this 3K, K here, another K, a third K. Well, the strategy we can use, or the pattern we can use to assemble local K to a global K is, let me change the color, is, for example, so we put all the local elements into the global matrix. The way to put it there is, like, for example, if we want to put this element K3 into the global element, and we can label this local element by U3, U4 row, and the U3, U4 column. So for this U3, K3, and we can find this location, which is U3, U3. And here, if we also label the global matrix as U1, U2, U3, U4, and this K3 will be put at U3, U3, which is a location here, U3 and U3. That will be K3. And similarly, see, I've changed another color. So if I want to put this element into the matrix, not clear, change purple. So if I want to put this into the global matrix, find its location, also label it U1, U2, U3, U1, U3, okay? For this one is 1 and 3. And then for this element is also labeled as U3, U3, so I need to find U3 and U3 again, and that will locate at the same place. So if the 2 local elements are located in the same place in the global element, we can add them up. Okay, and then one by one, you can put all the local elements into a global element. So if manually to put them into it, when the problem become complicated, is become tedious. But for computer, because once you have a pattern, you tell the rule to the computer, they can easily do it. Okay, and then eventually we'll get a global matrix. If I put all the numbers into it, that's the global matrix we have. Right, so This is global K, and the displacement is unknown. U1, U2, U3, U4 is unknown, and F1, F2, F3, F4 is external force applied to the system. Right, so the next step to solve this problem, we can apply boundary condition to it to simplify the problem. So without a boundary condition, we cannot solve this equation because this equation is a singular equation. So we have to apply a boundary condition. And then the way to apply boundary conditions is to look at the problem again. So what we have here is we have two fixed points. So nodal 1, so U1 equals 0, U2 will be 0, 2. And then we applied force on node 3 and node 4. So we have 200 and 100 Newton at 4, 200 Newton and 3. Well, in this way, we can put all this information into it. So we know that U1 0, U2 0. If U1, U2 is 0, and these two equations we don't need anymore. And also because U1, U2 are 0, and we don't need these two elements anymore. So we end up with a smaller local global matrix and two displacement vector and two external force vector. So by applying boundary condition, so the equation we have is 340 minus 160 minus 160, 160, and then we have two displacement U3, U4, and then we have two nodal force, which is 200 and 100. So by solving this equation, we can get the displacement of U3 and U4. Okay, and then the problem solved. And this is a quiz problem we left with in last lecture, and then we'll continue to look at today's topic. Today's topic is the energy method. So, and we will apply this method to a simple 1D spring system. Okay, the energy method is also called vibrational method. It's a more general method, and it set up the foundation of FEA. So the reason is the energy method can be easily scaled up to 3D. Although last lecture we have learned stiffness method, apply stiff method to derive the stiff matrix for the spring system. And you will see that when the problem become more and more complicated, energy method become more powerful. All right, so, and then the energy method is based on the principle is called minimum potential energy, which is stated as, well, of all the geometrically possible shapes that a body can assume, and the true one is the shape that will lead to a minimum value of the total potential energy. So an example shown here is if we have a beam which is supported by two ends and we apply force in the middle, well, and the beam will deform it might deform in different ways, but theoretically or physically, the only one deformation is possible. That is when the total energy of the system reach minimum. Okay, and now they come to the question that what is total potential energy? How to define total potential energy? Right. Then come to the next slide. Here we define the total potential energy. Okay, the total potential energy for static structural system is defined as the sum of the internal energy, so internal strain energy, and the potential energy of external force. So you can imagine that, for example, for the beam problem, we apply force to a beam with two ends fixed, and then, well, there will be deformation in the beam, and that deformation will lead to an internal force, which is stress, and also deformation. And that internal force and deformation will lead to an internal strain energy. So there will be positive strain energy stored in the system. And also because we apply external force, so we applied external force to the system on top, and that external force will do work to the beam, and which is also lead to the potential energy. So in this case, because we do positive work to the system, and the potential energy the external force, the potential energy will be a negative value. Okay, as a summary, so we have the total potential energy is defined as the internal energy because of the internal force at deformation, and the potential energy of the external force is defined as the external force applied to the system, and they will do the work to the system, and then we will lead to a potential energy. Right, so to make it more clear, and we apply to one spring system. So if we have a spring, and this is we assume that this is a linear spring, means the force is generated proportional to the deformation. So K times X. K will be the stiffness of the spring. Well, before to derive its internal strain energy and the potential energy of external force, and we first look at the relation between work and the potential energy. So work equals minus it's a negative potential energy. So and that's based on if the potential energy can transform to work, and in total the work and the potential energy should be zero, the conservation of energy. So the conservation energy work plus potential energy equals zero, and then that leads to the work equals minus potential energy. And we also know that work can be defined by force times distance, and that leads to the potential energy lead to minus force times displacement. Okay, we'll use this relation to derive the potential energy for internal force and external force. Well, for external force, that is the force applied to the end of the spring. So the other end is fixed. So and there will be displacement at this node at this end. As a result, we apply force and there's displacement, and the work done by this force will be F times X. And notice that this force is applied external force is a constant value. Once a constant value, we can directly apply the force times distance relation. And that leads to the potential energy, which is negative work, is negative force times X. So we do positive work to the system, external force do positive work to the system, and that means and the potential energy of the external force will be a negative value. Right, and then we look at the internal force. So the internal force, a little bit tricky here. The reason is, so the internal force, Fx, will change with the magnitude. Okay, magnitude will proportional to the deformation, and will change with the deformation. So that means at different x, the internal force will be a different value. So as a result, when we calculate the work, we cannot use a constant force to calculate the work. Instead, we need to use calculus. That means every time when we calculate the work, so we do it locally or in infinitesimal deformation. So we generate a small deformation by this force. When the deformation is very, very small, and we can assume that is constant. Okay, so that's a small work by the small deformation and all that internal force. Okay, and then the total work in terms of calculus is integration of the small work because of small deformation and integration from zero to final deformation. Okay, so and the work is done from 0 to x, the internal force, and we also noted that although the magnitude is kx, the internal force in the spring will go in this direction. So if we define x, this is a positive direction, the internal force is negative minus x, which lead to minus kx dx. Well, that lead to the internal energy equals negative work, as we have defined at the very beginning, is negative 0x kx minus kx dx, and minus contact each other, so become positive. So 0x kx and dx. After the integration, we have 1 over 2 kx squared. Well, that's well known that internal energy for a spring, for deformed spring. So, and then in total potential energy. So total potential energy represent, here we use pi to represent total potential energy, will be a function of x and equal to 1 over 2 kx squared minus f times x, whereas the internal potential energy whereas the external potential energy, or the potential energy over the external force. Right, once we get the total potential energy, and then I recall that FEM is based on the minimum of the principal and the minimum potential energy, and mean that, well, the equilibrium status of the structure is when this potential energy reach minimum. Right, okay, so to minimize this potential energy, we look at the math basics to find minimum for a function. So let's use an example to help you understand this, to set up the big picture. So if we have a function, let's see that y is a function of x. Let's see there's a parabolic shape is x squared minus 2x plus 1. Well, we know that this is a parabolic shape. We can easily sketch it 2D, which is x, y coordinate, and the y will change with x, and it pretty much look like this. This is a parabolic shape. Well, the minimum of y, which is the principal minimum potential energy we will use, we want to minimize it. Well, theoretically, well, from the photo, from this sketch of the curve, we know that the minimized point is on the bottom here. And notice that at this point, and the mathematics tell us that at this point, the slope is 0. Or the gradient is 0. And the slope here, mathematically, you can write as dy dx. Slope equals 0 means dy dx equals 0. So we can use this equation to get the minimum point. And for this case, dy dx is, well, 2x minus 2 and 0. This is dy dx. And equals 0 lead to x equals 1. So that tells us that when x equals 1, this equation or this function is minimized. Okay, that's a review of math tools to find the minimum for a function, and then we come back to our problem. The principal and minimum potential energy tell us that of all the possible deformations that the spring can assume, the true one is the minimum when the total potential energy reach minimum. Okay, that means mathematically, so we have derived that the total potential energy equals pi equals U plus external force caused potential energy. Well, we try to minimize this function. Find x that minimizes pi. Well, mathematically it's easy, right? So the pi is slope or derivative equals 0. Okay, so that leads to first term derivative is become kx, second term minus f equals 0, and which lead to x equals f over k. So that means when the deformation of the spring equals f over k, and the total potential energy reaches a minimum, and that's the true deformation that the spring can assume. Well, some of you may also notice that we take all the trouble to get the total potential energy. We minimize it, we reach a very straightforward conclusion or trivial conclusion, x equals f over k. Because based on force analysis, which is how we apply the stiffness method. We call the stiffness method. In this method, we do a force analysis, and then we get the matrix equation, and in that we apply force analysis. That means if we apply the stiffness method for this system, this conclusion is so obvious. So for force analysis, we know that internal force magnitude must equal the external force. Kx equals F. That means the deformation must be F over K. So if we do a force analysis with the foundational stiffness method, and we can directly reach this conclusion. And again, why we take all the trouble to reach the conclusion through energy method is through a simple problem that we want to show you that what is total potential energy and how to apply the principle of minimum potential energy. And you might get another sense that the energy method has no advantage when applied to a simple system. But when the system becomes complicated, the stiff method will become too mathematically hard to deal with, and the energy method will show its advantage. Okay, and then now look at the example. And this example will associate with today's quiz. You can see the quiz at the last slide. The example here is, well, if the spring, so everything is the same as shown in the previous example. So the only thing we change is when the spring is nonlinear, means the deformation and force relation changed. Fx instead of equals k times x is equals kx squared, and the k and f are given 100 pound per inch, f 500 pound. So the problem is express the total potential energy. So to practice you how to get the total potential energy of a system, and then use the potential energy principle, minimum potential energy principle to obtain the true or equivalent value of displacement. All right, so let's derive the total potential energy for the system, which equals the internal potential energy, external potential energy. So for internal potential energy, U equals kx squared dx integration from 0 to x. That's the internal potential energy for the system. The reason we apply integration because the internal force will change with the deformation. So it's not a constant value. And that's why I apply integration. So as a result, this will lead to k over 3x cubed. This is the internal potential energy and the external potential energy. So we apply force and cause the deformation of displacement at x. So that will lead to minus F times x. This minus because, well, potential energy equals negative work done by this force. So that's where this negative value comes from. F times x is work minus work is potential energy. So in total will lead to pi total potential energy equals k over 3 x third minus fx. Well, to minimize the potential energy, we get d pi over dx equals 0, which lead to kx squared minus f equals 0, and then x equals f over x square root, or k square root. So you plug the number into it, you can get the equilibrium displacement for the system. Well, again, this is a energy method to solve the problem. If you use stiffness method or force analysis method, it's so straightforward because if you apply stiffness method, Fx at the balance point should be equals external force, which lead to kx squared equals f, and then x equals square root fk. So the point of the problem is to help you practice how to calculate the total potential energy for a system, and which will extend to a more complex system. Right. And the last piece of the class, we'll apply energy method and derive the equation for a simple spring system. Derive its matrix form. So for a 1D spring, we can, in general, we can write in a way that we have two nodes, I and J. There are two nodes, and we use displacement at these two nodes to describe the deformation of the system. And the deformation is caused by external force, nodal force applied on the node. So Fi and Fj. So for such a system, we can apply the total energy, the principle of minimum energy method to derive this is a matrix form stiffness equation. Right. So the internal strain energy U equals, well, again, it's y over 2 and the k times deformation. The deformation, if you use node displacement to describe it, is uj minus ui squared. And the potential energy reaction of force is the external force applied on the node. So we have two nodes and two external forces acting on it. So the first node acting on the first node I will cause a potential energy, and another node Fj, Uj. And then that leads to the total potential energy, which is U plus external potential energy. Okay, so, and the next step is to minimize it. Okay, so here I write down this total potential energy, which I copied from the previous slide. Uj minus Ui squared minus Fi Ui Fj Uj. Well, next step to minimize it, but before doing that, we notice that for this problem, we have two variables. So this total potential energy is a function of Ui and Uj. Ui the Uj. Ui Uj. So we minimize the potential energy based on two variables. And well, for two variables, and we should have partial pi over partial ui equals 0, and partial pi over partial uj is 0. And for the first derivative equals 0, we'll get an equation that is k times uj minus ui, and then minus 1, because that's a coefficient with ui for the first term, and then minus fi, that's derivative about ui. So fg uj will disappear because it's derivative about ui. Similarly, for the second derivative, we get k times uj minus ui, and then minus fj equals 0. Or we write into a range of the terms, we'll put fi, fg to other side, and what we get is k ui minus k uj equals fi, and then minus k ui plus k uj equals fj. Well, there's two equations, and you know computer. To solve it, computer will write in the matrix form. We help to write in matrix form. We get is k minus k and k over ui uj equals fi fj. Well, looks familiar, right? So for this part, this equation is what we derived in last lecture based on stiffness method. Okay, so and use the energy method, we derive the same element equation in matrix format. And well, from now on, and we'll go to the chapter 2 and the other chapters, we'll see that we'll apply energy method instead of using stiffness method, because energy method become much powerful when deal with complicated systems. All right. Summary: we have learned principle of minimum potential energy. We apply that to a 1D spring system, and we derive the stiffness equation. And then I will take time to work on this quiz problem. The quiz problem, you notice that there's very similar to the practice problem. The only difference is this time the nonlinear spring is equals k to times x cubed, right? So for this quiz, I have extended the quiz time because the technical issue we didn't. Well, I'm not able to access the online system this morning, so I record this video, and then you can look at the video. And for the quiz, used to do tonight, but I extend to tomorrow midnight. All right, so I'll stop here. I will see you next week.